Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. if on a YouTube channel, you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right, hello everybody.
Hello, hello.
Welcome to another episode of Ask Us Anything about electrochemistry with the new introduction. Still very happy to have our new introduction as opposed to always having the the ACS 2018.
ACS 2018. You know, I miss it. I miss hearing you in the old style video, you know, talking about 2018 that you're always so critical of yourself.
I know. I do try to elevate this live stream to try and have it do more things, make it more relevant, more current, things of that nature.
Yeah. It's not just the live stream though. It's like your videos have just gotten more polished and
that's true.
and better over the years. And then it was actually torturous for you to listen to this old waiting video.
Yes.
That had some of the funny Dr. Redux, what do you call them?
The Dr. Redux miniseries.
Yeah, those are pretty funny actually. Those were good back in the day. But,
back in the day.
But it was, and you know, like actually even the earlier part of that video, because you made that video and it was like 60 seconds long, 60 minutes long, is long, you know.
Oh yes,
waiting
video.
And some of it was like, oh, I don't even have my hair that way anymore. Or like,
yeah,
you know, your facial hair, even your look.
Yeah,
it's like,
yeah,
don't even look the same.
They don't even look the same.
No.
So, but luckily the original idea was to have like, if there was going to be people waiting for the live stream to start, then this thing can be 45 minutes. We just and people can just start to ask questions and see, put the questions in. We could start working on them. But most people don't show up to an event until the very last minute most of the time.
That does happen. That's true. Yeah. So sometimes you end up waiting. I mean, I do webinars. The same thing kind of tends to happen. It's like, you know, the beginning, you always try to delay it by a minute or so because people don't filter in right away. And then as you're going, you're waiting, and then questions come. And sometimes the questions like something I talked about in the first 10 minutes, but they weren't there. Hey, you know, it's fine. All's fair, I suppose. But if you were on time, you would have heard it.
Yeah.
But, you know, I can't imagine. It's the benefit and the curse of being online, because, you know, in a real class, you know, back in my day when I was in school, which was so long ago because I'm ancient, it's you know, you would be embarrassed to physically walk into the classroom, I don't know, 20 minutes late or something. The professor would stare at you, and, you know,
everyone would stare at you.
And unless you really like the attention, I guess, you know, then it would be embarrassing. So all that is to say, welcome, which is not at all what it is to say, but everyone, please feel free to ask questions anytime. I know we're sort of, you know, talking and being silly right now, but this is definitely a place for you to ask anything about electrochemistry, as it suggests. You know, my good friend Alex here always used to do the intro, which now is part of this video. And so for those of you who are probably have joined us in the past, maybe you're not accustomed to the video giving all the stuff that you used to say. So we tried to incorporate it that way, which was a nice, that way you don't have to remember all the things.
You don't have to remember all the things. It can just be said, and then we can just go straight into answering questions and things like that. But one thing I will mention before we jump right into questions, and please type your questions in. We will get to them as soon as we can. I'm very happy that earlier this week I finally launched the introduction to chronoamperometry video. That was a long time coming. I think I started working on that in January of this year, and then by February I needed to like switch gears, do all this workshop stuff, and then it wasn't until like the end of August that like I'm actually back in North Carolina and can work on it. So finally did it and worked on it, finally got it finished, and so it's out there, and I appreciate everybody who likes this content and wants us to make more. I plan on making more videos about this kind of stuff.
Yes.
So, yeah.
Yeah, that's what we do. We're a media company. We make electrodes and rotators and potentiostats and all this good stuff, but mostly we're a media company.
Yeah.
You know, we have podcasts and live streams and videos, and we are internet people. We don't really exist in real life, even though Alex goes to workshops and we go to trade shows. We're actually just virtual people.
Yeah,
we're fake internet people. So I hope you appreciate the internet content that we're bringing you. That's our whole entire purpose at this point in time.
Yes. Yeah.
I would make things easier, actually.
What if we were
just that was our whole job?
Oh, just doing this?
Yeah.
Oh, absolutely.
Yeah.
100%. Like if you are
I would have so many more webinars out. And everything.
So many more webinars, so many more videos, just all kinds of stuff. And we could increase production value, all that stuff.
We have other things we have to do.
Other things we have
sometimes.
To do. Yes.
So George, good to see you again. Yes, of course we remember you. You're still here live helping people. Yes, we're trying anyway, spreading knowledge.
Mm-hmm.
And I do recall your name, and you'll have to forgive me for not remembering specifics of your questions. It's probably been 30 episodes.
Yeah, it might have been 30 episodes.
Which is about half a year, if I'm guessing. Maybe you last came 4 or 5 months ago. But good to see you again. Appreciate appreciate you joining us in the comment here. Emilio has asked a quick question here. Is the Pine Research Wave Now wireless potentiostat compatible with other software? So PalmSense's PS Trace. No, it isn't. Our potentiostats are exclusive to our software, Aftermath. There's no other way to control a Pine Research potentiostat other than through our software. So unfortunately, you're not going to be able to control it using PalmSense's software. I'm not sure how common that is, to be honest. I mean, I suppose it's, I mean, maybe PalmSense has some ability to control other companies with theirs, or maybe they allow theirs to be controlled by, but I'm not aware of any situation like that. To be honest, there are some companies, not all, where they
like OEM.
No, API is it?
I don't know if API is unique to internet things, but I think the idea is still, I don't know enough about it.
In other words, there's some equipments that have a special sort of a feature where they let you control it with, an aggregate software. And a lot of times it's because they're doing their taxes over here and they're watering the garden over here and they're doing electrochemistry over here and they want one computer to control everything, right? And it's like, anyway, that sometimes can be done, but by a wide, I suppose, margin, it appears to me that most potentiostat companies, we write our own software platforms for everything, and that's the primary way to control them. So and if you need any help getting Aftermath or working, if it's not working properly for you or one way or another, we can help. Right. I mean, contact us and we can help you. You want to, if you like PS Trace, probably a good reason for doing so. And there might be a perfectly valid way to do something in our software that you enjoy about theirs, for example. And we're happy to kind of show you how to do that if that's the case. So,
yeah. All right. Next question is from Sergio. He asks, what books do you recommend for learning about electrochemistry and electrochemical engineering? I have a basic knowledge about redox reactions from my course of analytical chemistry. Well, we got this question a fair number of times. So this book here is Electrochemical Methods, Fundamentals and Applications. It's the 3rd edition. Sometimes this book is referred to as, it's sometimes called Bard and Faulkner, who are the two, there are 3 authors here, but the first 2 authors. This is the 3rd edition of the book. They have 2 other ones. This is sometimes, oddly enough, referred to as the Bible of electrochemistry. It is very comprehensive. It's a very comprehensive book. I do find personally, when I talk to people, they find this book to be somewhat difficult to read and understand. It is, it's written as an extremely comprehensive textbook on electrochemistry, with lots of derivations of electrochemistry equations, lots of, it goes through the gamut of everything. But for basic knowledge, like even if you've taken like an analytical chemistry class, and you want to know more about electrochemistry, there are other books. Give me a second to find some. Kissinger. So there is a book called Laboratory. Let me actually share my screen for this one. So there is this book called Laboratory Techniques in Electroanalytical Chemistry. This is.
Let me help. I think it's not sharing.
Oh, it's not sharing?
I got it.
You got it?
There you go.
Thank you. Yeah, so Laboratory Techniques in Electroanalytical Chemistry. This is by Pete Kissinger and William Heinemann. I have found this book to be much better from like a practical perspective. It goes over some of the theory, but it also gives you like how to do some experiments. So I do believe that this is a very good book for doing electrochemistry. I'd say the last book let's see if I can find it just in Amazon, so I don't have to share my screen. It's called Electrochemical Engineering, and it's by Fuller. Yes, so this book, Electrochemical Engineering, I think this book by Thomas Fuller and John Harb is actually quite good. It goes over the what you really need for fundamental electrochemistry, but then it actually goes into a lot of like how do you do certain calculations. Like if you're given a lot of data on a thing, how do you make a calculation on it? So I would also recommend this book as well. I think it's written quite well. It goes over a lot of different subjects. Also another kind of textbook that it's kind of fun in a way. Like before each chapter, they have like a little history about a famous electrochemist, and so you can learn a little bit of history as well. So those are my suggestions on books right now for electrochemistry. Hopefully that was helpful, Sergio. So let us know if you have any further questions.
Mm-hmm. So Buami has a question, and I asked for a bit of a follow-up because it'll be a little tough to answer. I can give a little bit of advice, but I work on electrochemical detection of drugs with a modified electrode like GCE, so I assume glassy carbon electrode. Mm-hmm. And I always find a problem with the electrode response. It never is stable. How can I stabilize the modified electrode response? So the main question I have for you, Buami, if you can, this is my question to you, is can you describe the process of modifying? Because you know, a modified electrode that's something like a film, like a thin film, is a different kind of a thing than if you're doing like an electrode deposition as a modification, or is it a physical vapor deposition? Is it a ALD? Is it something like a polymerization, right? So I guess I would like some clarification on how you're modifying it, because, you know, in the absence of some specifics, it's sort of like a circular answer is what I have for you, which is to say, oh, well, why, you know, my electrode is having trouble being stable because I'm modifying it. And it's like, yeah, that's why, you know, like, I know that's a weird way to answer. That isn't really much of an answer, but the point is, like, modifying electrode surfaces is often a kind of a thing that just requires practice, trial and error. A lot of times, like every specific kind of subfield of electrochemistry in particular, but even just chemistry in general, there's a lot of like tricks of the trade or things that you might not know going into it that just take time to know, or you'll like find someone who happens to know and they'll tell you, oh, actually, if you just like cut the corner of this or construct it in this order, or you do it on a Tuesday when it's raining. Like there's like weird things like that. Like I've talked to a lot of people about a lot of different stuff. I've experienced in the battery world with this. I know a bunch of people who have done, for instance, some organic electrochemistry and electrosynthesis and things like that. And there's a lot of weird, like, oh, well, if you don't put the thing at an angle in the cell, it doesn't work for whatever. It's like, why? What does it even matter? It's like, well, we just found that it works, and there's all sorts of stuff like that. So the modification of an electrode is one of those things that falls into that category. If for example you're making a thin film, like casting a thing and drying it or whatever, I know a lot about that process. I might be able to give you some advice. If it's a electropolymerization, I might be able to comment on that a little bit. If it's like some sort of a chemical polymer, electrodeposition, excuse me, I know some things about that. If it's like a polymerization or it's some, I don't know, something like that, I might not have as much knowledge about that to help you. But I'll sort of, we'll watch for, it looks like just a response as I speak. I modified sometimes with CV forming a film, or chronoamperometry when I use two potential. So it does sound like some sort of electrochemical modification. I think it's very possible that you are making some sort of a film that is not sticking properly for one reason or another, or you have not made enough of a film. So like, for example, if you're doing chronoamperometry by applying a certain potential and for some period of time to make a film, is your potential high enough to oxidize or reduce whatever it is onto your surface, right? Some of those specifics you might want to investigate, look into. Is the integration under the current versus time curve? That will be the charge. You can correlate the charge of your chronoamperogram. Speaking of which, go watch Alex's new video
that's right.
on chronoamperometry. But the area under the current versus time chronoamperogram will give you the charge. Is that charge perfectly well correlated to the process that is the depositing of the film? Not exactly. There's some maybe attributed to double layer or things like that, although it fades over time. Anyway, that is like charge that you can say, oh, well, this many coulombs went to this film, and I know the stoichiometry of this process. You should be able to work out roughly how thick my film is. Maybe you're not depositing long enough. Maybe your film isn't very thick. And then, there are certain things where, especially with glassy carbon, I will say, for instance, like when you have a platinum electrode, you can deposit copper on it pretty easily, and it makes a nice film of copper, and it won't flake off. In fact, the only good ways to get it off a lot of the times is to use something like Piranha solution and physically get it off, or you reverse the electrochemical process afterwards to divest the film. Glassy carbon, on the other hand, doesn't always make a very good film. And even in some cases, when you like reduce something to make like a metal film on the glassy carbon, it's only kind of fizzy-sorbed because the glassy carbon just doesn't bond that well with, like, let's say you just have like, I'm making this up. Like, I don't even know how, like zinc ions in solution, and you reduce it and, you get a film of zinc on there. It might flake off the next set of tests you do. Like, okay, you put it in
solvent.
Yeah, exactly. That might only be somewhat loosely physically absorbed, fizzy-sorbed, as we might say, or adsorbed, whatever the right terminology is. And that subsequent tests or a different solution, as Alex said, sometimes it'll fall off and flake off. So I do suspect probably that something like that is occurring. And so it's something, the process of your film formation needs to be investigated, and possibly a different substrate needs to be used, honestly, because glassy carbon works well for the thin film deposition, because a lot of times you use something like Nafion, which basically is a binder. It acts like a glue to keep your thing in place. Even that's not foolproof, but it works pretty well. The electro deposition often can have a tough time with glassy carbon. for whatever reason, it just doesn't have the greatest ability to do that all the time. So I suspect you might look into those, I don't know, those aspects of it and see what you can do.
Mm-hmm.
So I guess we'll move on. I don't want to talk forever on the one thing here, but anyway, follow up, Buami, if you want to ask more specific about it, I can try to give some more advice, but that's kind of what I can share on that at the moment. So
yeah. So the next question is from George. And George says, I want to buy a new potentiostat, and the best I've used so far is Biologic, but they are extremely expensive. Can you suggest another company?
We have the company for you, George.
Yeah, I don't know, Neil. This might be really hard for us to figure out what.
Do I know any companies that make potentiostats? Alex? Do you know any?
Hey,
there's this logo on your shirt. I think it's
yeah, from some of these, you know what? I look at some of the giveaways we have, and and whether it's one of our pens, it reminds me of the company that.
I mean, you just teed us up way too easily here. I can't help but think you're doing it on purpose, George, which we appreciate. But yes, our company makes potentiostats.
Pine Research Instrumentation also makes potentiostats. And depending on what you're trying to do with them, I think you'll find that ours are more at a better price point.
Yes, and technically more than capable of accomplishing what you're looking to do.
Yeah.
If I do say so myself, I have nothing bad to say about Biologic. They make excellent instruments.
Yeah, they do.
But we are aware that in some cases, probably they can be on the pricier side for people who are doing a certain kind of lab setup. Let's just say, you don't have all the funding in the world. We are more than happy to try to meet you on price point for some of these kinds of situations. So
yeah, absolutely. So
please reach out to us. I'll put our email. Yeah, I was just gonna put our email Pine. I'll put email. Wait, sorry. Neil and Alex at Pine Research. So here is our email. If you did want to get a quotation or something like that, you can send us an email. We can kind of talk about that. This live stream is not, to be fair, we're not actually trying to market and push stuff. It just, the question was so perfect, but
we do it very subtly. We just hope that you just by over time you'll be like, I work with the Pine guys. I trust them.
We should we should do is we need to get like a video. This is like actually live. You're actually watching and listening to us live, but like we need to work on that. That thing that like they used to push subtle things onto people, like evil companies pushing you to buy their stuff or something. Like every 8 seconds a video pops up and it just goes Pine, Pine. Or something.
Buy our stuff.
Buy our stuff.
Buy our stuff.
Just peppering it into like normal conversation. And it's like, you didn't see that coming. It's totally subliminal. You'll never see it coming.
Never see it coming.
That's right. And then you'll wake up in a cold sweat at 3 o'clock in the morning, be like, I have to buy a potentiostat.
That was from that episode of the podcast when we interviewed Bill.
Oh man,
it's just so I wake up early, wake up at night, just think about CVs.
The best part of that whole episode was what you did with that.
Oh yeah, I did that.
Oh man, yeah. My boss from graduate school, Bill Mustaine, he's a great man at the University of South Carolina, and we did him very, very wrong.
We did him.
He's the Bill. If you ever see this, Bill, I love you and you're the best, but I'm so sorry. We interviewed him in one of our podcasts, so check out our podcast. It's on our YouTube channel, or it's on wherever you get podcasts. And whichever episode did I forget, we interviewed him. And Alex had the great idea, he said a bunch of funny stuff throughout, the interview. We can make this very funny fake advertisement. We need to come up with some kind
of ad. And I was just like, what thing can we do from it? And I'm like, I think we can go with
it's so funny. I won't give it away. No, don't give it away. Don't give it away. It's funny.
I just want to figure out what episode it was.
It's episode 9, 10, or 11. It's towards the
end. Episode 11.
11.
Episode 11.
Episode 11 of our podcast. Check it. The ad after the interview before the game we play.
Yeah.
It's like the funniest thing I've ever heard.
It's great.
And we did Bill pretty raw.
Pretty raw.
But it's so worth it. It was so funny. That's phenomenal. Okay, sorry. We'll move on here. So
the next question is from Mike Energy.
Hello, Mr. Energy.
Yeah.
How to deal?
Call me Mike.
Call me Mike. We'll call him Mike. Yeah.
Call Mike.
How to deal with difficulty in reproducibility in and I think he clarified even he means EChem.
Oh, EChem measurements.
Yeah, in EChem measurements like batteries.
Oh, yeah.
Actually, to a certain extent, this answer is similar to what I just talked about, which is the reproducibility is most likely related to the not electrochemistry stuff. Unfortunately, batteries in particular are very much in that class of things where there's a lot of stuff that you just like need to know, and if you don't know, it won't work quite well. So I'm just as a couple of random examples, if you happen to be doing like lithium ion batteries in particular, this will help you maybe, but like when you're making coin cells or you're making cylindrical cells, or any kind of cell, and you're doing like a half cell kind of a thing, you often use lithium metal itself as the other electrode. So it's like an infinite lithium source, right? If you're studying an anode, you'll use lithium metal as the cathode because it gives you basically like a perfect cathode, let's just say, so you can study the specifics of your anode, and vice versa for the cathode. Okay. Before you make the battery with your lithium metal, you need to physically rub the lithium. That sounds weird out of context, but I mean it. Literally get like not sharp tool, but like some, I don't even know what I use. What did I use?
Like a razor blade?
Not a razor, not too sharp. Maybe like the edge of a razor blade, but like almost like a spatula kind of. And literally like polish is not the right word because it's not really polishing, but like there is a kind of oxide-ish. I'm not sure if it's oxide exactly because it's usually in a glove box, you know. So there's not much, if any, oxygen or moisture in the glove box. Otherwise, the lithium will not behave very, very well, right? But there's almost like a, what's the word? Patina. You know that term? It's like when you have like steel, but it's like faded. It's not shiny. You say patina. I never know how to say that word. Patina. It's a thing.
Okay. Yeah.
So
you have told me a new word.
Yeah. I never know how to say it. Now I'm curious. Patina. That will appear on the lithium metal. Patina. It's a thin layer that variously forms on the surface of copper, brass, bronze, silver metals. It's it's like not shiny and whatever. And so when you polish and sort of scrape the lithium surface on both sides and the edges and everything before you put it in the battery, it will behave better. Okay. So like, okay, that helps. That makes your reproducibility better. But why would you know to do that? Nobody ever says to do that. You just know or you don't know. Having the right amount of electrolyte, if maybe you don't have enough electrolyte because not enough electrolyte will cause the diffusional stuff to be slower, and that will cause inconsistencies. It is possible that you're trying to scan too fast or too slow, or I don't know, something like that. Okay. And so some of the electrochemistry can be adjusted, but most likely it has to do with the construction of whatever battery form you're doing. Another one, for example, is the loading, right? So if you're doing a Dr. Blade method or a spray method, or painting your catalyst onto your current collector, how well and how accurately are you sort of adding your catalyst layer? Then maybe you'll heat it and dry it, add another one, heat it, dry it. You mass before and after. You're getting the mass of it. How well do you know you're loading? Is it how many milligrams per centimeter squared, right? If you have too much inconsistency there, you're going to be way off. Like if you have double the amount of milligrams, you think you're charging at C/2, you're actually charging at C/4 because you have more grams or something like that. So stuff like that is going to make a difference. Really work on the fabrication process. Another sort of anecdote I'll tell, which is also, I think it made the cut of the podcast in a serious note with the interview with Bill. One of the things that he shared, which he did in his lab, I believe after I left, but it was shortly after I left because there was a project where he was working on some electrolyzers or something like that. And everybody in the field, I say that most people in the field, for instance, are looking at, let me get a new catalyst. Let me get a new support. Let me make a new material to make this electrolyzer, this fuel cell, this battery better. And Bill basically spent like a year adjusting nothing about the catalyst, but only adjusting the other stuff that nobody talks about, like the humidity of the cell, the flow rates, the pressure, the fabrication process of putting the fuel cell or the electrolyzer together. How many times should you torque the screws and tighten it down? All that kind of seemingly auxiliary stuff. And he was able to improve the performance by like tenfold or something even better by just playing with those. And that is, ridiculous when you think about, like, I could get better performance if I just had a better control over my wrench. Like, it's ridiculous. It seems ridiculous, but those things are really overlooked a lot of the time. So I think sometimes we're looking for this sort of magic answer, and a lot of times it's something as silly as that. So those are just maybe a bit of a long-winded way to kind of a few specific things with batteries that are from my experience. Maybe that'll help you. Maybe it helps somebody out there. But really, as always, this is just research, right? We're always looking for reproducibility, and it takes time.
Let's see. So the next question is from Emilio. It says, on another question that I have, if you're able to cover it, is there a way to save a whole plot while a test is still running into something like Excel files to show change in a compound over time? So let's see. Okay, is there a way to save a whole
I think
plot?
an aftermath, basically.
Yeah.
While a test is running, I don't believe you can like copy the data that's capturing
already.
That is actually a feature that is it exists, but not for you. we actually do have that, but it's not released yet. I'll just put it that way. So it's something that is, for example, very common with battery people. You often need to, like, you're doing like a charge discharge thing for like a month, and at 2 weeks in, you want to check it out and see how things are changing, and it's still running. You need to be able to kind of access the data and whatever. I'm not saying that other folks don't do that as well in the electroanalytical, whatever.
Yeah.
So that's definitely a good, thing to do. The two answers I have is that it's coming in the near future. It's not, that particular feature is not ready in Aftermath right now, but there is a way to get that kind of a thing effectively, which is to break up your experiment into multiple sub experiments. You can reduce the lag time in between. Like if you have 100 CVs, I'll just make this up, right? Okay, whatever. And you want to check, and it's just going back and forth 100 times or 50 times, whatever it is, right? And you want to check like every 10th of them. Well, you could just do 5 or 10, sets of 10 at a time with zero like delay time in between. So it will act as though it's going 100 of them back to back, but every 10 CVs, it plugs the data like it's done, and it reports it, so you can look at the data from those, and you can break up, do a sequence. You can do like program it to do this many, save the data, this many, save the data. So in Aftermath in particular, you can do things like that will accomplish effectively what you're asking to do in the meantime, until this new special kind of live grabbing of data at any moment is available. So that's what I can tell you.
All right, let's see.
Looks like they were asking about the book. You got that?
Yep, I got that.
Is SECM, I think is
yeah.
Right?
SECM asks, could you briefly explain about the relationship between resolution and electrolyte conductivity, and in SECM? In SVET, it is directly related, and I am curious if it is also the case for SECM. I'm not very familiar with SVET. I just looked it up. Scanning vibrating electrode, just as technique.
I don't know
it
SVET.
Looks similar. Generally speaking, though, and I don't have a lot of experience, but when we talk about resolution, so in scanning electrochemical microscopy, you're taking an electrode as a tip, and you use a piezoelectric device to have the tip approach the surface, and the feedback loop associated with getting a good distance from the electrode to the tip is based on a feedback current from a redox molecule in the solution, where if you apply a positive potential to induce the oxidation reaction, and that this is called, it's a redox mediator. So that's a redox mediator. So I don't need to use my hands. I can use. I was like, why am I?
We always do this drawing.
Yeah, I was
drawing in
drawing
outer
in space. It's like,
Yeah.
wait a minute.
If only we had some sort of computerized device. Look, you do.
Wait. We have this thing.
We
So
have technology.
we have technology that allows us to do this. So actually, that's not what it is. I don't want to make a graph. I need to. So people can see this, correct?
Yes, I checked it for you.
So the general principle behind SECM is you have some kind of tip. This is your electrode. This is like your E1 electrode, E1. And then you have your substrate, which is your E2 electrode. So you can control these two electrodes. And then you have a redox mediator here. And so you have O goes to the electrode, gets an electron, it becomes R. But then when R gets close to E2, it then gets oxidized back to O. And so you have this feedback current between these two. And this, the feedback current is based on how close the distance between these two electrodes are, E1 and E2. Okay, so once you get the electrode close to the surface where this feedback current occurs, you're in the diffusion layer length when this feedback current occurs. This gives you a very close distance, and then you can use your piezoelectric device to move either the tip or the substrate around, and then you can start doing imaging. So when we talk about resolution, and I'm going to, because I can't draw very well, I will say. So when we talk about resolution, we're talking about the map. We're talking specifically about the image that is formed, because this is an imaging technique. So I'm going to try to draw this as carefully as I can, as three-dimensionally as I can. So this is just distance. And maybe the distance is maybe it's in millimeter. Let's say it's in micrometers. So maybe this distance is micrometers, and this is also micrometers. And you get these little points. It's like I got a current here, I got a current here, got a current here. I'm moving around. And maybe I see different things. Maybe I see like, oh, there's actually like a step terrace here, or some mountains, or mountains, like on an electrode or something on your E2. You have these weird shapes and stuff. The resolution, and of course, correct me if I'm wrong, SECM, if this is what you were talking about. But the resolution has to do with how well defined is this spot, this square that you can see. Is it like, can I see things on the nanometer area scale? Can I see things on the fractions of micron area scale? Can I resolve a single atom, right? Maybe my current response is just based on like when I scan across a single atom, I actually can get like a huge current. And in that case, I have like single atom resolution, right? If I have an electrocatalytic activity going on. So resolution always has to do typically with how well resolved, how well do I get these little tiny points when I move from here to here. And the resolution is based on in some cases, the electronics of your piezoelectric device that controls this. And more importantly, that scientists care about is the tip of your E1 electrode. This will define, in some ways, the resolution, because if you have, define resolution, resolution. So you can imagine if I have an electrode tip, but it's kind of chunky here, it's kind of flat. The current is this big. That's the size. That's the resolution I can get. It's this big. But if it's very, very sharp and I measure current here, my resolution is going to be much, much better. I'm going to have a higher resolution based on the tip in my SECM experiment. And then when we talk about electrolyte conductivity, really has to do with I kind of think of that as more of a bulk electrolyte type of thing. I don't know enough about like does electrolyte conductivity play a role in this resolution, because the current that you're measuring is just based on this redox reaction that's occurring from this redox mediator. But the electrolyte conductivity is just like, well, how concentrated, what's the conductivity of your supporting electrolyte in your electrochemical cell. So that is my understanding of those two. I would need to learn a little bit more about scanning vibrating electrode, about the scanning vibrating electrode technique, to really know if those two are related. But that's how I think about resolution and electrolyte conductivity. So I hope that it's helpful. Please let me know if that was helpful, or whether or not I got your question right, or I got your question wrong.
There's no other comments, so I'm taking that to be it's 100% right.
Yes, thank you.
It's just my very unbiased opinion, but yes. It looks like Ashik has a question. How can I convert current into current density? It's actually quite simple. So, I mean, literally, the literal process is dividing current by area, and that is how you get it. I'll show you in our software practically. That may not be the program you're using, but maybe it's something similar. So just for instance, am I sharing properly? I guess I am. Okay.
Yep.
So here's our software aftermath, and here's like a CV. It's just a normal sort of, I think it's ruthenium hexamine duct. Okay. You see, I have current on the y-axis, and I have potential on the x-axis. And so if I wanted to convert this to current density in our software, it's sort of a two-step thing here. You can see we have a convenient I assume you can see the right-click menu. Is that showing up? Yeah, right. The right-click menu is not showing
the
up?
right-click menu
doesn't show up. I'm gonna try to share screen. I hope this doesn't do anything weird. Yeah, the menus don't show up, which is a bit weird. This might be like trippy for a second. Okay, so like sharing the screen of the screen. Okay.
Yeah.
So now I think you're seeing it properly. Do you see the right-click menu?
Yes, I do. I
okay.
see the yes.
It's sort of pointless if you can't see that. Okay.
Yeah.
So in this menu here, you see there's an option for change units. Okay, so I can do that. And so this is quite simple. I'm going to perform this on the Y data. That's the current data. And I want to replace the tray. I want to replace it with current density. So in the list here, there's current density. You can see that what it's doing is it's dividing by like length squared, basically. And so when I do that, it just changes the unit to current density. And then basically what I want to do is mathematically convert it. So I changed the unit. Now I need to do the operation. So for instance, if this was the current that I measured, but I know that my, current was whatever. Well, now I have to do a math operation. I'm going to divide the y data, and I'm going to replace the trace. And if my, area was whatever 0.01 square meters, I have no idea what the number. I'm just making up a number. Okay, so don't worry about the number specifically here. Well, there you go. Now I've just divided, and here I go. So that now I have current density, and that's it. I mean, it's literally that simple. It's just an area normalized current. Okay. And so if you're doing this in Excel, you would just divide by the current column everywhere by whatever the amount of your area is in whatever unit, meters or centimeters squared, whatever it is. And there you go. That's quite literally it. So I just thought I'd show you a practical example, but that's the answer for you.
Yeah.
Okay.
So it looks like the next question
is Nuruddin.
Okay. I work on high temperature steam electrolysis. A problem I am trying to solve is that our steam supply causes pulses and makes the EIS at low frequencies very noisy. What could I do to mitigate this? Continues by saying, would potentiostatic EIS be better than galvanostatic? The problem with increasing the perturbation, while it improves the data at low frequencies, it creates nonlinearity at high frequencies. So I need to think about this. Part of my initial thought is to do something to adjust the steam electrolysis steam supply. If you can put a like a buffer or something in the way of, I don't know enough about the system, but I'm wondering
I think it's strange you're doing galvanostatic already.
Oh.
Why aren't you doing potentiostatic impedance to begin with? So I think most probably, yes, potentiostatic impedance would be better. I'm surprised you're not already doing potentiostatic impedance. Something like steam electrolysis would lend itself better to potentiostatic impedance from the beginning. And there may not be, based on your explanation here, which is to say nonlinearity at high frequency is contending with drift or noise at low frequency, there may not be a sweet spot of the amplitude, basically. In other words, too small of an amplitude is probably going to give you a lot of noise at low frequency. Too big an amplitude is going to cause it to be nonlinear. But there may be a sweet spot. And so to a certain extent, you may end up having a situation of just searching for that sweet spot, right? Fully acknowledging that it might not be possible. I acknowledge that. Okay. But don't give up right away is my point. So I would try, you've seen many papers use galvanostatic. Interesting. The trouble with galvanostatic is that, especially with what I'm just saying now, which is that you are modifying the amplitude to try to find a sweet spot between noise and nonlinearity, right? As you do that, the potential response is going to be varying pretty wildly, particularly at the low frequencies. So, for instance, as the if you think of Ohm's law, V is equal to IR, right? As R goes up, V goes up. Okay. So at the lower frequencies for a particular application of a current, as the resistance or the impedance goes up, the voltage response goes up. So at low frequencies, it's actually interesting. I think that the nonlinearity thing is a problem. It could be a problem at low frequencies as well. But that's going to probably cause you to have some noise, in addition to the fact that you may end up, if your potential goes up or down like crazy, you're doing steam electrolysis that requires a particular potential, right? If your potential goes too low, for instance, you might not be doing the electrolysis in part of your impedance experiment. That might be leading to the noise as well, because it's like if you're applying a current or a potential so that you're electrolyzing the steam, but the wide amplitude is causing it to dip below a critical potential at some frequencies, where the steam electrolysis is actually turning on and off like electrochemically, that could lead to some of the instability in your results. And so I don't know what SOCTSQA guidelines. So there's obviously some sort of standards associated with this. Okay, it suggests 3 to 30 milliamp per centimeter squared and 10 to 30 millivolts. Those sound like reasonable numbers. Again, the thing here is that if you're doing a specific process like steam electrolysis, it's like if you're doing galvanostatic at a 3 milliamp per centimeter squared which multiply by the centimeter squared, that gives you some amount of milliamps. Let's say you have 1 centimeter squared. So that means your amplitude is 3 milliamps up and down, right? But around what? Is it around 0? Is your baseline 0? Because is at 0 current at baseline, that's open circuit potential. Is steam electrolysis happening at open circuit potential? Because if it isn't, you're not doing very much. Compared to having a DC bias, right? So you can't have a DC bias on a galvanostatic impedance test. Those are different modes of operation. You can have a current bias. So for instance, if the device you're using again, I'm just making for the numbers just to be easier. You have 1 centimeter squared. Okay. I'm just going to work in current to try to make it simpler. So if I apply 10 milliamps, I assume I'm lowering the voltage of the device, or whatever the voltage of the device will move in such a way that steam electrolysis is happening. Like, for sure it's happening. I'm getting, the products of that. As part of my polarization curve, I might need to apply either galvanostatic impedance with a 10 milliamp, or in the case of 10, it might be minus 10. It depends on how you have it connected. Hopefully you kind of know how you're doing that one way or another. Normally in a potentiostat, when you connect the working electrode to the cathode, the current is negative, just for what it's worth. But in any case, you apply 10 milliamp or 10 or minus 10 milliamp a baseline, and then you have 2 or 3 milliamps on top of it. So that's not a DC bias. That's it's not AC bias, but I guess it's a DC bias. I'm sorry. DC is a direct current. It is a DC, but I was thinking DC in terms of potential. But yes, it's a DC bias galvanostatically. And that will make the steam, electrolysis happen actively. And then you're testing the impedance of that process. But you have to be careful, because if your amplitude is so big at the end, let's say you have a volt to work with, and by applying 10 milliamps, you're getting 800 millivolts, and one volt is the max. Well, if it's swinging 100 millivolts up and down, 200 millivolts up and down, 300 millivolts up and down because of the current, perturbation, that's way too much, right? You're going to be doing who knows what. You might be over polarizing the cell and causing things to go. If it goes below 0, you'll be polarizing it backwards. You could cause severe damage. Like, galvanostatic impedance is helpful sometimes, and it may be fine to do that. You just have to be careful, because how far you're swinging the voltage might be causing you to move from like the transition to the diffusion region. You might not be getting consistent results because your resultant potential is moving too far. And I hope you have an instrument that helps you see the raw data, so you can see just how far the resultant potential or current is. Not all instruments show you the raw, like, sine wave data when you're doing impedance, so that can make it difficult too. But hopefully you can kind of work through those, I guess, troubleshooting things. And yes, I do suggest a DC bias, especially if you're trying to induce the electrolysis process. You might not be doing that adequately at open circuit or with no DC bias.
All right. Very good. The next question is from Hussein. Hello, we are doing Tafel tests, and we sometimes get 2 or more corrosion potentials, mostly in cathodic branch. Can you suggest anything? We're using biologic potentiostats. It seems strange you would get 2, like, because I was under the impression that the Tafel plots, like, they diverge they diverge, and then you have I
assume it means linear 2 slopes, like 2 slopes.
You'd have to have like 2 slopes, I presume.
Yeah, that can happen
for that to be the case. So 2. So you have branches. You have your line. You have one intercept, but then if your slope changes, you may have a second.
I assume he means something like this. I'm just gonna guess.
Yeah,
I assume it's something like this. If this is your,
that would be
this
voltage
is
over potential.
Yeah, this is voltage or over potential. Either
yeah,
way.
yeah.
This is current. That with a cathodic one, for instance, this is open circuit potential right here. Basically, if this is I at 0 or whatever, this might be log of I or whatever. But anyway, the point is, something like that, right? So there's like you might get like slope 1 here, and then slope 2 here.
Yeah.
And so it's like, okay, well, if I'm trying to find the intersection between with that to find like a corrosion like E core, you're looking for like where these intersect. And so it's like, is that intersection here? Right?
Yeah.
Or here, because there's 2 different slopes. Which one do you use? It can get murky.
Yeah.
Anyway, that's kind of what I assume you're talking about. You say 2 potentials. I assume you mean 2 slopes. If you're talking about a Tafel plot, because actually this is log.
Log
if it's a Tafel plot anyway.
But
the point of it being, of course, that it's unclear in this case. So did I talk about this last week? I feel like I talked about this last week.
Tafel plots?
Yeah, no, I feel like I talked about this with respect to someone. Where did I answer this? I know this is not germane to the question at the moment. I answered this recently.
Yes, you did talk about because someone was it's always the same question. How do you determine the Tafel slope or something like that?
I think I talked about it with someone asked it with respect to the anodic one, and that there's 2. Oh yeah, they were asking about steel, and they said I'm getting like 2 different slopes on the anodic side, and I basically was like, yeah, that's mostly just passivation.
Yeah, that's a passivation.
As far as on the cathodic side, I'm not positive, to be honest with you, but it might be something similar. I don't know if you can get a passivation layer with cathodic as well. Maybe
via reduction
some other process.
Corrosion
is more of an oxidative process, of course. So it's a bit counterintuitive to think about the cathodic process. I think one of 2 things is the answer. One of them is that you're using a biologic potentiostat. No, I'm just kidding. No, I think one of 2 things is very possibly the cause. One of them is that there's people will describe this in the literature when they look at Tafel analyses and Tafel plots, and I have my own feelings about these things, but like a lot of Tafel plots you'll find in the literature have like sometimes more than 1, sometimes more than 2 sections where it's like it's a slope here, and then it go a little further in potential down, and then there's this slope, and then there's like and it's like they'll describe it as these different processes at different potentials. You might have a different kinetic situation going on. I don't know. Maybe you have the first oxidation, and then you polarize it more, and you get you hit the E0 of a different the next
another process that's
happening. There's a lot of times you get like 3 peaks in a thing. I don't know, whatever. Right. So it's entirely possible that you have multiple processes that you're probing their kinetics through your Tafel plot. And for example, you get a slope of 120 millivolts per decade for the first one, and that indicates that your first process was a 1 electron transfer, whatever fast irreversible thing. And then at the next slope, a little further away, it means you polarize it further, and you get a slope of 60 millivolts per decade. And so that suggests that there's a second 2 electron transfer process at this potential range. I'm just making this up, but like those are the kinds of analyses that folks will do in the literature, for instance, when they find this. So that's the first possibility, and that might be valid. The second, frankly, might be that there is error. You're improperly studying a Tafel, or improperly making a Tafel plot, let's just say, because as I have discussed pretty frequently on this live stream and in my webinars, for instance, the Tafel equation, and therefore the Tafel slope, and therefore a Tafel plot, requires 100% pure kinetic data. It is a direct manipulation of the Butler-Volmer equation, which is a theoretical expression that relates the overpotential and kinetic current, nothing else. So a lot of times what folks will do is take an LSV or a CV, and flip the axes and take the log of the current and make a Tafel plot. You can manipulate data however you want, but you did not make a Tafel plot, because that's not kinetic current. That's just current. And that current contains diffusion and non-Faradaic processes and non-kinetic processes. And unless you're able to know, for instance, a lot of times the trick here is to scan really slowly. So you discharge all capacitors all the time. You mostly get rid of non-Faradaic and diffusional effects as much as possible. And you assume that most of the current, if not all the current, is a result of kinetics only. When you scan it like 1 millivolt a second or slower, a lot of times those assumptions are they're close enough to being valid, let's just say. But it may be in your case that that's not accurate. And so you are not eliminating all non-kinetic contributions to the current. And so the appearance or the illusion of multiple slopes or multiple kinds of regions in your Tafel plot is not real. It is a result of using a Tafel transformation improperly. So those are the two answers I have for you. If you want to follow up, you're welcome to. I don't know if you have any, oh, well, I did this, and so maybe that is why, and I'm happy to discuss that further. But those are the two possibilities I have for you.
All right, we have a question from Shruti
on LinkedIn.
From LinkedIn. Yeah, so thank you for asking us the question on LinkedIn. It took a while, but we did finally get to you. Is it possible to have more results in galvanostatic charge discharge than in CV for a supercapacitor? More results. So you can always generate more data by just doing the experiment more. Like you can increase the number of cycles, sort of say. Do you get more information per se? I don't know if that's what you're really after. Do you get more information if you do galvanostatic charge discharge on a supercapacitor than doing cyclic voltammetry? There's a part of me that I kind of want to say CV is going to give you more.
But yeah, I tend to feel that way also. For a couple reasons. One of them is that I to be honest, I'm actually somewhat surprised, and we were talking about this earlier with someone, a customer of ours is doing some galvanic GCD kind of tests on capacitors and trying to go up and then down and up and down. Capacitors are characterized very often by extremely quick charging and discharging. As compared with a battery that delivers smaller amounts of energy over a long period of time, longer, let's just say. A capacitor is generally something that will deliver a larger amount of energy over a short period of time, right? And so cyclic voltammetry, now, in a similar way, you can do GCD at different rates by applying a different magnitude of current, right? So you can apply 1 milliamp and then 10 milliamps and then 100 milliamps, and it will charge or discharge faster at higher current rates. The same kind of phenomenon can be accomplished with CV by scanning faster, right? Because ultimately, with a true supercapacitor, the CV, to your point, is giving you all of the information you need. Basically, it's the CV response is entirely non-Faradaic, which is capacitive, like only, and it's exactly what you want. Right. And the current is equal to the capacitance times the scan rate. And so effectively, as you scan faster, the current gets larger, and you can back out a measure, the capacitance very directly. And so with galvanostatic charge discharge, you can get the capacitance or the capacity in terms of like, I have a material, for example, that has this theoretical capacity. One way or another, I can determine that. I know how to do it for batteries. I don't know exactly how to do it for capacitors. It might be a similar process, but anyway, I know how many like coulombs per gram or whatever it is, and then I can charge it up and say, did I get that many coulombs? You can get an efficiency. So that might be something that GCD will give you. In particular, that CV may not be exactly the same, but the CV will allow you to get a measurement of like how many farads this thing actually has. Like, I think it should have this many. This is how much it actually has. It has this many farads per gram or whatever of capacitance, and CV is really good at that. And it's also quicker, and you get to the scanning, scanning at a bunch of different scan rates, they all overlap on each other. It makes a nice plot for a paper, to be perfectly honest. It's a nice looking kind of a plot. GCD on capacitors is over really fast, especially as you start going to high charge discharge rates, because like I said, a capacitor is already something that is designed to deliver a large amount of energy quickly. And so unless you're applying a very small current for the capacity of your supercapacitor, it's probably going to charge and discharge pretty fast. And so you just don't have as much data to kind of look through. I'm always kind of surprised when people are doing a lot of GCD on supercapacitors. I always kind of assumed that CV was a better diagnostic, but
we actually we have a little bit of a follow-up, I believe. So Shruti's on LinkedIn, but also on YouTube.
Yeah, I saw there was a follow-up question here. So
yeah, I think this is related. In GCD, when we have nonlinear graph, we use integral formulas to calculate specific capacitance. But in that formula, we have limits. But if the potential, we have limits. But if potential window is from -5 to 5, then the answer will be 0. She wants to know how that's the case for specific capacitance.
Well, the answer is 0, because if you're integrating and it crosses over the x-axis, you're adding a positive and a negative, and that's just math at this point, right? So what you're talking about is less to do scientifically with what's happening and more to do with mathematics, most probably. So for instance, if you have your integration and you are crossing from, I don't know which direction, but if this is +5 and this is -5, right? And your plot is going whatever, it doesn't even matter. And you're getting the area underneath the curve. The area integration is technically this area plus this area, right? Well, this area is negative and this area is positive. So possibly if what you're trying to do is just get this total area, you might have to take the like absolute value of the area. That might be what you're looking for specifically. I'm not 100% positive, but I mean, do you understand? Like if it's on this side of 0, this number here is negative, right? And this number here is positive. So it's just going to make it look like nothing's happening, but that's not necessarily true, I suppose. And that might be another reason, for instance, to say, well, GCD is kind of tripping you up a little because you're kind of going from -5 to +5. Like you can do a CV from -5 to +5 and you'll get, a nice sort of envelope or whatever. And then you can bisect it, get this distance is the current, right? And as I said before, current of a CV is equal to the capacity times the scan rate in millivolts per second or whatever, right? And so you can just you can solve directly for your capacitance, or how many farads. You could divide by the mass, get farads per gram, whatever. Farads per centimeter squared. It doesn't matter. Specific capacitance or just capacitance. What's the relationship? Remind me. What's the relationship between coulombs and farads? Is a volt? I don't know why I always forget this.
You mean like Faraday's constant coulombs and farads?
No. Like I always forget. I don't know why.
Just looking at it. So
coulombs.
A
coulomb over a farad times a volt is
a coulomb. Yeah.
So I'm just with what I have here. So for example, because the difference of GCD is you're getting basically it's milliamp hours, but it's coulombs.
Yeah, it's coulomb. Oh, okay.
So and this is farads, and they only differ by basically like scan rate or the voltage or something. So
yeah.
I'm just saying, if you're trying to convert, for instance, from a GCD,
you're only getting charge.
Yeah, from a GCD, you're getting Q, right?
Yeah,
Q in coulombs.
Yeah.
Right. From CV, you're getting C. I know this is like coulombs. I'm saying this the capacitance in farads. So that's sort of these are similar metrics, I guess, but one of them is they're different.
Yeah. I mean, it's that same equation, like I equals C times scan rate. The integral of that is charge is equal to the integral with respect to time is then charge is equal to coulombs times volts.
Right.
So it's all the same.
Q is equal to C times volts.
Times just volts. Yeah.
Right.
Instead of scan rate.
Right.
So
you can sort of compare that way, I suppose.
Yeah. They in principle they should be the same. The capacitance of the supercapacitor should be the same, ideally, no matter what technique you're using.
Yeah, of course.
Generally speaking.
Anyway,
So
I don't know. Hopefully that's. Let me just. There's no follow up here. Yeah, feel free to follow up on YouTube or on LinkedIn, Shruti, if there's a need here. But I think that kind of covers, hopefully, to some degree, what you're asking here. So.
Yeah. Okay.
Divya has a question about GCD.
I think we kind of inadvertently. I think we kind of just talked about this by answering Shruti's question. Divya, maybe?
Sort of. I can answer this a little bit. In the calculation of specific capacitance or capacity in GCD, how do we get the current value? I'll show you an example. I'm not sure if this is exactly what you're asking, but it's similar kind of a phenomenon. But so how do I get the current value? So it kind of sounds like what you're asking, and maybe correct me if I'm wrong, Divya, is like something like, I'm trying to figure out how much current do I add for this much C rate or this milliamp hours per gram or this whatever.
Wait, are you showing? You have the PowerPoint up, right?
I know. I was just checking if there was any follow-up question, I guess.
Oh, yeah. Okay. Just making sure.
Yeah, no, you're good. So let's just say your capacitance is, 1 milliamp hour per gram. If you're trying to find out what the current should be, you have to know what the rate you're trying to do is, what the rate. So let's just say the rate of discharge is, let's just say, C over 2. Okay. So that means I take 1 milliamp hour per gram, divide it by 2. So I need to apply 0.5 milliamps per gram. I'm making the hour unit go away. Don't worry too much about why. First is the rate, though. So again, I'm sort of walking through an exercise that like a battery researcher might do, or a supercapacitor researcher might do. If you're trying to figure out, like, I know, for example, the specific capacity of my battery or my device, how much current do I type into the software to make it go? Well, first is, hey, I want to do C over 2. Okay. If I have 1 milliamp hour per gram capacity, I need to apply 0.5 milliamps. Now, let's say I know how many grams I have, right? So for 1 gram, I'm making all the numbers super easy, right? 0.5 milliamps per gram times 1 gram equals 0.5 milliamps. So there is an answer. Okay. So for example, if I know how many milliamp hours per gram, my thing is, I know what charging rate I want to do, and I know how many grams I have. That's how many milliamps I will plug into the software program and tell it to do. That's how you calculate the current. I assume that's your question.
I think that's the question.
So if that isn't your question, please follow up and I can try to walk through a different calculation, I suppose.
Yeah.
I think that's what you're asking, Divya. So if that isn't the case, please follow up.
Yeah. Hirak is saying, I guess the question is, what is the perfect condition, applied potential or frequency, to record EIS, potentiogalvanostatic, during electrocatalysis? So oxygen evolution reaction or hydrogen evolution reaction. I guess, what are the perfect conditions? So what would be the applied potential, the frequency? Should it be done potentiostatically? Should it be done galvanostatically during an electrocatalysis experiment?
Yeah, probably potentiostatically. Probably something like 10 millivolts peak amplitude, and probably something like let's just say 100 kilohertz to 1 hertz or 0.1 hertz. We'll probably do it. That's pretty general, and a lot of experiments are going to fall under that category. In the case of OER and HER, though, I will say a lot of times you may need to tweak those. You might need to err on the side of increasing the amplitude more, like 15 or 20 millivolts. And the reason being that it becomes pretty unstable, especially as you start generating a lot of gas. There's a natural difficulty built into OER and HER, which is that the O and the H that is being E'd is messing with you, right? You're evolving gas on an electrode surface that breaks apart the solid liquid interface because it's gaseous, and then it hopefully leaves, doesn't stick around. If it sticks around as a bubble, that's even more of a problem. So sometimes it adds noise, right? And increasing the amplitude is a way to improve the signal to noise ratio sometimes. But that's somewhere to start, right? See what your results look like. Apply a DC bias that is either low enough for HER or high enough for OER, and apply those limits that I said around that baseline and adjust them from there is my advice, I suppose.
He's asking, he has a follow-up, how to select the DC voltage for EIS.
Well, for OER, it's high, right? The potential for oxygen evolution reaction is 1.23 volts. In whatever versus SHE under typical conditions. So it'll vary if you're an acid or base. It'll move depending on what reference electrode you're at. But if you're trying to do OER, in theory, you have to be higher than that potential. Is that right? Did I say it's 1.23 volts? I think, right? Because hydrogen is 0.
Positive 1.23 volts for oxygen evolution.
Oxygen evolution reaction.
It's in water. Yeah.
Yeah, it's the opposite of the oxygen reduction reaction. Right?
Yes.
So, yeah.
Oxygen evolution reaction is the opposite.
No, that's backwards.
Yeah. But you're applying the positive potential in water to oxidize water to oxygen.
Yeah.
That gets evolved, and then hydrogen reduction.
Hydrogen's at 0. It's like
standard. It's like SHE.
Right. Yeah. Again, the exact potential will vary when with
whatever your catalyst system is, your pH,
the over potential of your catalyst. If your catalyst is terrible, it'll take more potential.
I do a CV just to see where does the potential start to ramp up,
right?
And then pick a point, pick some potential after that, or during the ramp up. That's where stuff is happening. Of course, it needs to be made. You have to make sure it's stable at that potential, and then do EIS. Then
right. So practically, you do a cyclic voltammogram is a good idea. Check where it pops up at the positive potential for OER. Pick something along that uptick, basically, that indicates that your catalyst and thermodynamics are satisfied so that the oxygen evolution reaction is occurring. And then similarly on the negative end, that's where HER is happening. You can pick potential down there for HER as your bias, your baseline, whatever you want to call it. So
we have, I don't know if you want to go back to the Shruti has some follow-up because we just finished talking a little bit about GCD. She says that she's generally getting a huge difference in the calculation of the specific capacitance between GCD and CV. And I think she's using this equation. The specific capacitance, and I'm sure you correct us if I'm wrong, is equal to 2 times the current times the mass times the integral of the voltage divided by the voltage squared, limit from the initial to the final voltage. That is I'm assuming that's the method with galvanostatic charge discharge because or is that the limit with galvanostat? No, because in galvanostatic charge discharge, you're setting the current.
No, so yeah, so if you're setting the current, the integration is actually not. You don't even have to integrate. It's very simple. If you're applying a certain current for a certain amount of time, that current times that time is the coulombs. Like that's it. That's the coulombs. So you're doing a lot of unnecessary integration, basically. For a GCD, the current you applied for how long you applied it is coulombs. Then, I guess divide by mass if you want to get specific.
It still needs to be divided by the voltage to give you the capacitance.
To give you capacitance.
To give you capacitance in farads.
Just right. So I'm talking about charge.
Yeah.
I call it capacity. So pardon the terminology. I'm thinking like a battery person. Well, coulombs is the same as milliamp hours or amp hours. It's another, and it's the word we use as battery weirdos is capacity, and it's charge, right? Okay, so specific charge or specific capacity would just be that number divided by the mass. The problem comes with multiplying by the voltage, because what voltage is the question?
Yeah, that's right. Because
the voltage is changing.
So the voltage is changing during that experiment.
Right. So I don't know which voltage to multiply by. And you're asking about an integration. So it would be it's
a little bit of there's definitely some interesting unit analysis.
I have to think this through.
But like when you do cyclic voltammetry, for example, Shruti, you can do a series of scan rates, and you'll see your kind of rectangles like grow, and you can do a linear regression. That's probably one of the best ways to figure out what the capacitance is, and then you just divide it by the mass, the grams. Like, so grams, that's all like constant. But that is like the method for using CV to measure specific capacitance. But for GCD, the method, let's see.
It's like you're dividing by the volts, but I don't know. I don't know if I know precisely what volt, like that what I just described, right?
Yeah.
Current times the time is the charge that you did your GCD at. The nonlinear part of it is irrelevant. Like the voltage is going to be moving at some rate that may not be linear. That's fine. That doesn't matter. The current you're applying is probably constant, and that's what makes GCD nice, because the charge, I'm trying to use the wording that's not a battery person, the capacity or the charge that you passed is very easy to calculate, because it's just the current times the time. But I don't know what voltage to divide by to get. If you divide that charge by volts, you get farads.
I'm also kind of, I'm thinking about it from maybe her equation's correct in the sense that, because it takes the integral out. So like I
think the tricky thing is, so for example, if you think about it, the current that you apply, if you divide by scan rate by volts per second, you will get farads.
So if this is voltage,
current divided by scan rate gives you capacitance, excuse me.
And so, but if this is if this is a GCD, because we're talking, this ultimately just sounds like we're talking about like a area calculation, right?
Kind of.
So
but it's not. The problem you have here is that I is constant throughout the whole thing, right? So it's not even really, you're looking at a voltage versus time plot is what you're looking at when you're looking at GCD.
Oh, when you're looking at GCD?
It's voltage versus time.
Oh, it's voltage versus time. Oh, yeah. Okay. All right. So GCD, right? So I'm trying to learn.
I know it's chronopotentiometry, right? And so the output of a chronopotentiometry, which is GCD, is just another name for chronopotentiometry, is potential versus time.
Yeah. So your voltage is here. This is constant.
Yeah, so it's some value.
Constant. And then let's just say the graph looks like this. Is that okay?
It'll go all in one direction, but sure, yeah, like it won't go up and then down, basically.
Okay, so all right, so should I say it looks like
it'll go down, but not at exact the same rate.
So will it look like this?
No, let me draw it.
Oh, wah. Okay, all right, you draw. You draw.
I'll draw.
But at the same time, I'm trying to think of like it's a this is like a math problem.
So you'll have time down here, you'll have potential over here, and it's like I is equal to, 1 milliamp, whatever, and so it'll just be like that.
Okay. Is this formal? Is this? So she's just giving us a comment. Just is this formal? Is right?
Formula. Yeah, she's asking if that formula was right
for nonlinear.
So okay. The thing is, right here's the things, and this is something I haven't done with supercapacitors. With batteries, you don't really talk much about the capacitance.
Mm-hmm.
So this is where I'm kind of getting. I'm not 100% sure. Okay, and it's also a reason to reiterate what we said before. I think CV is probably better to use because with a CV, all right. So this is GCD, right?
Mm-hmm.
I applied some current and I get something that looks like this, whatever. Okay, fine. This is CV, right? I have current and potential and I get something that looks like this, right?
Yeah.
I have the expression here that the capacitance, I'm trying to say the right words here,
yeah.
right? In farads is equal to the current divided by the scan rate. Okay.
Mm-hmm.
So this is equivalent right here. We have farads are equal to current, which is coulombs per second, divided by scan rate, which is volts per second. So it's divided by volts per second. So the seconds, right? The seconds cancel.
Mm-hmm.
And I have coulombs per volt is equal to farad. So dimensionally, that's what you see here, right?
Yeah. Yeah.
All right. Follow me here. All right.
Yeah.
At this GCD, I can get coulombs very easily because this took 10 seconds.
Mm-hmm.
And I applied 1 milliamp. So 1 milliamp, right?
Yeah.
Times 10 seconds gives me 1 millicoulomb. Sorry, 10 millicoulombs because math is hard. Right.
Yeah.
But it's easy, right? I got the coulombs exactly. Now to get to farads, so that is the charge, the capacity, whatever word you want to call it.
Yeah.
If I want to get to capacity, another approach to this, capacitance. Gosh, I can't say the right word. So sorry.
It's all good.
To get to farads, I have to divide this by volts. Well, what volt, right?
Mm-hmm.
Another option is I take instead this current. I have a constant current the whole time, 1 milliamp, and I have to divide by a scan rate. Well, this is basically a plot of scan rate, but it's not linear.
It's a non-linear. Yeah.
So now what I have is two things. One is I could probably take a linear regression of my GCD plot and get an effective scan rate, get some millivolts per second, average of this plot, and then plug that in here, divide my current by my effective scan rate, and that will give me how many farads. And you can compare this with the CV one. Okay, so that's one approach. But it should be fairly evident here that doing this approach right here is less accurate in some sense than this one, because my scan rate is known in the CV. I'm actually setting it and determining it. It actually is on a, it's some number.
Yeah. So here's the only thing is, and this is a guess, because the supercapacitor is the same. My guess is that on the CV side, your current would not look like a nice rectangle.
Right.
I think the shape would actually start to change a bit.
Okay. So that's a good point. So let me put it this way. I'll try to frame what you said in a different light.
Mm-hmm.
On the CV side, the current is less accurate, less controlled.
Okay.
On the GCD side, the scan rate is less controlled.
Yeah.
However, with the CV, by simply maybe increasing my window a little bit, like let's say it's so fast that this is like, it's like climbing or whatever.
Yeah.
I can adjust the parameters. I can maybe change the scan rate a little bit. I can increase the window and let it settle out more, go wider, a wider potential window.
Mm-hmm.
I can adjust some of the parameters that even if this current isn't perfectly flat,
Mm-hmm.
it's still pretty accurate. I can get half of this, I can bisect this CV and get a decent, there's some inaccuracy, but it's pretty easy to get a decent average of what that current is.
Yeah.
However, over here, there's almost no way that this GCD voltage versus time plot is going to be linear. Almost no way. Now, now maybe I'm wrong. Maybe it's pretty linear, but there's probably not a lot you can do necessarily, especially at different charge discharge rates, to get this potential and time curve to be a linear thing, such that there is more error in my estimation associated with using a average scan rate from the GCD than there is from using a rough current from the CV.
Yeah.
So again, it seems that CV is possibly more accurate from that perspective if you're calculating farads.
Yeah.
So I think that we've talked ourselves back to the same conclusion, which is that CV is probably more accurate for that. Now, GCD is perfectly good for calculating charge and the time it takes to charge up and down, and capacity, as the battery people tend to think of it as, which is charge, another name for charge, right? That's what GCD is good for. But I think that probably explains where you would extract numerically from the GCD to get an estimate of the farads, and it's probably not the most accurate thing to do. Is my suggestion. So
I mean, the hope is that the answers are close to each other.
Yeah, but I just suspect.
Totally off, but
I just suspect if one of them is more erroneous from that perspective, like how many farads this thing is, the GCD is going to be a little less accurate. It's going to be great for capacity charge because you know exactly how many coulombs it took, how much current over what time to get from one voltage to another. That's like ironclad. That's why it's a great test.
Yeah.
But the farads, exactly, impedance or CV is going to be better for that.
Oh yeah, well
so
just tell her to do EIS.
Yes. Well, now I'm adding another wrinkle in. But
now another wrinkle in.
I hope that is.
But hopefully, So hopefully that's helpful. There are a few questions. Some are so technically the next question in line is from a dual who just asks very simple, can you talk about future of lithium sulfur batteries? I don't know if you have anything to say, I think, about this. He doesn't actually ask any more like detail about it. I don't know if you want to say anything general, just because we do have some questions that are a little bit more.
Yeah, I don't have a lot to say, to be perfectly honest. I mean, I am a battery researcher by trade. My general opinion is that all battery technology should be researched as much as is possible, because the energy future of the world will involve batteries. It already involves batteries, and it will involve batteries more. And I am always in favor of a diversified approach to research of any and all technologies that are at least remotely feasible. And lithium sulfur batteries are certainly in that category. As far as specifically, I just don't know. I don't know of any commercialized applications of lithium sulfur batteries yet. There may be some, I'm not aware. I think maybe lithium sulfur is better for like larger scale storage kind of operations. I might be wrong about that. But lithium ion, obviously, even before lithium ion, it's the precursors to those were like NiCad or nickel metal hydride. Those got supplanted mostly by lithium ion. There's some sodium ion, there's some zinc ion batteries that are having some penetration. Lithium ion is the most common and most popular, right? But there's some people working on zinc and sodium as well. Some polymer batteries and air batteries as well might have some application. I think it's certainly feasible. I don't know of a huge amount of market penetration of lithium sulfur. I think there's some toxicity issues. Lithium sulfur is also quite a bit more complicated. It has a billion oxidation states, and it's a little bit of a tricky chemistry compared to some others. But beyond that, I don't have any real specific information. So I do apologize. I can't really give you like, well, exactly this is where it is and this is where it's going. I don't know enough to answer more specifically than what I just said.
Let's see. Next question is from NVS Praneeth. Consider I have a standard CV LSV curve from a photoelectrochemical process. To get the best contribution of light excitation in the photoelectrochemical reaction, what potential should I select? NSV also continues to say, related follow-up, do we get the electron lifetime at the interface from the Bode plot using the formula T is equal to 1 over 2 pi f, where f is the peak frequency, i.e. f is theta maximum. So generally speaking, and this is again just coming from like very limited experience, I would do as you have LSV or CV of this photoelectrochemical process. Ideally, you're also shining light on your working electrode during this process. The potential where you get the highest current should be the potential with which you see the best contribution of light excitation. My guess is that you are moving the potential or doing whatever band bending, whatever stuff, which I still am understanding more about. But you've moved the potential or the Fermi level of the semiconductor in such a way that the maximum amount of light, you are exciting the band gap of your semiconductor in your photoelectrochemical system. So at that potential, you should see the most current, in this case, the most photocurrent. And so that would be in your IV curve. It's the potential where you see the highest current. Now, I haven't seen too many of these CV or LSV curves for photoelectrochemical processes, but I would just imagine there should be one peak where you see the highest current. And this will be different than, say, the open circuit potential, but that's, I'd scan relatively slowly. Actually, you don't have to scan that slowly because you're dealing with a scan rate versus the speed of light. So speed of light's very fast. The process should be occurring.
It's a little quick.
It's a little fast. I do not think you will get any information on the electron lifetime at the interface from a Bode plot, because that.
So let me share.
Oh,
this
f
one.
is the frequency at theta max.
There's a parallel to this part of one of my webinars that I show. So I assume this is what you're referring to in some way. Is that the peak, for example, in a Nyquist plot, the frequency here? You said T is equal to 1 over 2 pi f. So I have 2 pi f. This is like
that's frequency. So 1 over frequency is just time.
Yeah, I mean, so the inverse of this is just the time in like radians per second. So you get seconds if you just invert it. Okay, so fine. So this is the radians per second. So inverse this, that's the time. Okay, so fine. So I don't know that I can speak specifically to it being related to electron time that specifically, but what I will say is that this time, this W omega P, is related to the both time constant and the capacitance. Okay, so if you have a semicircle, it's related to a Randall's element. A Randall's element has a resistor and a capacitor, and the RC, the resistance times the capacitance, is equivalent to the time constant, which is something related to a kinetics, which is like an electron time. There's something here. I don't know how it. I don't know.
Yeah.
You can take it further. There's something kind of there.
There's something, yeah.
But I don't know if it's exactly the answer to his question.
But like, I think NVS Praneeth is asking about how long is the electron in the conduction band before it relaxes back to the valence band.
Oh goodness, I don't know how we could answer that exactly.
Yeah, that's usually like a purely spectroscopic kind of like question.
Do you think there's any way that if there's impedance, that there's some Randall's response, somehow it's fast enough to measure something like that, and they can get a peak frequency that somehow you could relate this through a time constant of some sort in what we're seeing here? Is there any way that fits into the realm of possibility, or probably not? I'm just, the peak thing made me think of this slide, so that's why I brought it up.
No, absolutely. I think that your slide is correct in what it represents.
Yeah, sure.
Which is not what the electron lifetime is at the interface.
Fair.
I don't, but again, at the same time, NVS Praneeth, I don't think so. But if it's anything like, okay, the lifetime of the electrons in these things, well, actually, I don't even know a general order of magnitude.
Fast.
So like, so what is it, like fluorescence? Like when you have like those stickers that are on like a wall, like nightlight stickers and stuff. Like that is like a very, like, you create an excited state with the electron or the molecule, and then it very slowly decays, which is why you can see it, and the light lasts very long. That's like, seconds, minutes, hours. But a lot of these, like, I want to say the whole recombination, whatever thing, how long that lasts between like the electron hole pair separation before they combine. I feel like that, I think that happens. Yeah. So they are at the nanosecond time scale. Okay. So if it's the nanoscale time, if it's the nanoseconds time scale, you're probably not going to see it in EIS, because 1 megahertz is 1 megahertz at the fastest frequency is looking at like 1 microsecond or something like that. That's like double layer charging. So NVS Praneeth is asking, what is the time constant in your equation?
Micro to milliseconds.
So the time constant typically, is in the micro to milliseconds. It's the time it takes to charge the electrical double layer.
And what I showed, which is why I brought it up, because it's reminiscent of what you're talking about. I think there's some world where it's similar. That world is not the reality of our equipment collection time when it's nanoseconds, right? But there's something in theory where what I showed would be applicable, let's say. But again, the time constants are microseconds slowest, milliseconds, possibly seconds, depends on the value of the resistance, for instance, because a lot of times you can have a capacitance that's relatively small, which lends itself to a slow microsecond or millisecond time constant. However, the resistance can be so large in the case of like a non-aqueous solvent or some other stuff that you get like half a second or whatever. Right? And so there are some electrochemical systems where it can take 5 seconds to charge up the capacitance, or whatever, if the capacitance is big enough. And so, so we're talking, upwards of 7 to 9 orders of magnitudes difference, and it's a bit much.
It's strange. Like, this has been one of the interesting things about like electrochemistry and spectroscopy, or electrochemistry and photochemistry, is that spectroscopy and photochemistry happen on very, very fast time scales. Sometimes people are looking at femtosecond or picosecond, nanosecond spectroscopy to understand how does an electron move, or how does light move between different states. And electrochemical processes don't even happen until the electrical double layer is formed, and that's already on the micro to milliseconds time scale. So it's like, it's hard to do some of these ultra fast spectroelectrochemistry things.
The electrochemistry can't even physically happen until the other thing is over.
Right.
It's like,
yeah.
it's like, how do we sync these up?
It's done it 1,000 times before.
Yeah, exactly.
Before the
electrochemistry is even physically possible.
Yeah.
Like literally not physically possible until the double layer setup. So
yeah.
It's crazy.
It is kind of crazy.
Yeah.
Hopefully that's helpful. And we will continue. I'm going
I think
through.
Bawami basically was putting out some more. Needing more advice on stabilizing the electrode here, basically. And in my work, I have to form a film that contains polymer, noble metal, and ionic surfactant on a glassy carbon electrode. What are the things I should worry about to make that film give stable response? He appears to be in dire straits because he is graduating and really needs our help. Yeah. Trying to think of I already sort of tried to talk this through, right? I generalized advice. So you're doing some kind of electro deposition kind of a process, and so I mean I wonder if, for example, if you have like a two-step process, for instance, where let's say you have your glassy carbon electrode with solution that has your polymer precursor, whatever it is, I don't know, some salts and surfactants, whatever, and it involves applying a negative potential or a negative current for some period of time, and that forms a film. It seems to me again that you're up against a couple of things versus that glassy carbon sometimes has a tough time maintaining good adhesion, right? And so you might need to consider treating the glassy carbon before this. So you could try an activation process. We've talked about this in the past. Last week, I think we talked about it a lot. Try cycling the glassy carbon electrode in something like half molar sulfuric acid in a separate container before you do this deposition process. Try cycling your glassy carbon to relatively large potential window. You'll have to look up an activation process. It'll depend on the reference electrode and the pH of your solution, but you basically do CVs with a pretty wide potential range. It's an activation. It might improve the surface area of your glassy carbon such that it is more active for adhering or grabbing in a film and having it stay. So you could try something like that. You could try some sort of a physical process after your deposition. So like, again, the thin film process that I talked about often involves making an ink, inverting your electrode and depositing a drop onto your glassy carbon, letting it dry, and it makes a film. So this is not an electrodeposition process. This is like a physical deposition process. You literally make like an ink with some water, whatever particles, catalyst in it, and you get 10 to 20 microliters of a micropipetter, and you drop a drop onto the glassy carbon, let it dry. But what comes with that process sometimes is a second step where you drop some binder on top, and it acts like glue, and it will keep the film on. And so what you could try, for instance, if you're having a delamination process, which again, I don't totally know your process very, I can only give some ideas here, but if you're doing some sort of a electrodeposition and you get a film, but it's possibly falling off, you could try depositing a drop of Nafion suspension, some other kind of binder material on top after the electrodeposition, and letting it dry. Rinse it with water, for instance, get any extra salt away. Hopefully you still have a film there. It's not delaminating. And then drop some binder, like microliters of a binder on, let that dry. That might keep it in place. Maybe that's the thing that will help, because if the film is falling off, that might be the stability. Otherwise, as much as you would not necessarily want to do this for a commercial application, if you deposit less So let's say you're trying to deposit some amount of film. The more you deposit, the thicker the film will be, and the more likely it may be to delaminate or fall off. So if you do half as much, so if it says, if you're reading a procedure and it's like, okay, if I apply this much current for an hour, try doing it for 20 minutes instead, or 15 minutes. Try applying a thinner film, less of it. Maybe it'll stay on better, and you can still get results because you can normalize your result to the mass or the surface area that you get. So, for example, if you get, I'll just make these numbers up. Let's say you do like a electrode deposition for an hour, and you get 100 milligrams of active material on your surface. And then you try to do CV on whatever it is. Okay. Now let's say you do your electrode deposition for 15 minutes, and instead you get a quarter of that. You get 25 milligrams. Well, just divide your results by the mass, and you get a normalized current or normalized results, right? So you can normalize your results of the film by however much mass or surface area you got, but the thinner film might be less likely to fall off. It might be more firmly attached if it's not so thick, something like that. You can try things like that. I don't know if I have any other really like general advice without knowing specifics of it or anything like that. I mean, I don't know if you have anything else to add.
Yeah, no, it is hard to give specific advice from a somewhat general question. We have to guess a lot of things, but hopefully that was helpful.
I guess those are the two things I have for you.
Yeah.
Try making a thinner film, or try adding a binder on it, maybe. Otherwise, you might just be stuck. I know you're trying to graduate.
Yeah.
Welcome to grad school.
Yeah.
Everyone's always trying to graduate, and you never quite get there when you think you're going to. It's sort of life. But anyway,
sort of life.
Yeah. But you might be in a trial and error kind of a thing to work out the procedure. But those are just a couple of things you could try. I don't know what else I could say. I hope that you get there. I hope that you have success. And yeah, best of luck to you. I suppose I don't know what else I can tell you. So
yeah, I think we're basically out of time. Hussein had a little bit of a follow-up, which maybe I think he was again talking about the corrosion potentials where the ionic and the cathodic branches reach each other. I think we need to see the Tafel plots, perhaps, if they're non-symmetric, sort of say, to really kind of answer the question more, because your original question was about getting these two corrosion potentials, or getting two or more corrosion potentials.
Yeah, where they reach each other sounds like where those slopes intersect. That's what I'm interpreting it as, but maybe you don't mean that.
Yeah.
So you might mean something else. And I guess we'd have to kind of see where the ionic bridges reach each other. I mean, where they reach each other on like a Tafel plot is at it's where I equals 0. Like you base on these kinds of plot experiments. Basically, you do one of two things. You either start at open circuit potential where current is 0, and you scan positively and get the anodic side, and then you go back to OCP and you scan negatively and get the cathodic side.
Yeah.
Right. Or you just start at one end, like negative part, scan from there to 0, and then you keep scanning till you get to positive, and the part from the negative, current until it's 0 is the cathodic one, and then as soon as the current becomes positive, that's the anodic part. And because you take the logarithm of the current, it's all positive. You take the logarithm, so it's like the absolute value, basically. So like that's why they both like go out the same direction, right? From the plot, it's like, I can't draw this in the air, but it's like, they're thank you.
This way, or the breath going.
Exactly.
Way, or something like that.
So, the log of the current's always positive, and so they look like they sort of touch on the left part of the plot or something like that. But that's just because the current, it doesn't go through 0. The current, there's no it's all positive because it's a logarithm. So that's why we take the slope of the Tafel region, which is just usually the first linear observable linear area, after the polarization.
Yeah.
And that is the, cathodic and anodic Tafel regions. And then the slopes where those intersect is the E core and I core. So
yeah, I sometimes wonder whether or not the order in with which you measure them matters. Like,
I think it does.
Yeah, because like if you're creating some corrosion and then you're doing the
I always suggest to
cathodic.
People to do the cathodic one first.
Oh yeah, cathodic one first for
so
reduction.
Start at OCP, for example, scan negatively 200 or 300 millivolts or whatever it is. Depends on your system, but and then start at 0 and then do your anodic, because typically for a corrosion procedure, the anodic is where you're really corroding it most. And so if you do that first, you're corroding it intentionally to study it,
Yeah.
But you might be corroding it that affects the cathodic subsequent scan. Branch. So I almost always suggest starting with the cathodic one, because the anodic one is more likely to mess with the cathodic and not the other way around.
Yeah, that's right.
Yeah.
That's right. All right, I think that is. That's it. So thank you all for joining, and I probably need to make an outro video at some point.
Yeah, that would be cool.
I can work on that.
That'd be a nice little way to say goodbye, because right now we just go dark. We say goodbye and then we're gone, and it's abrupt, and it's a bit jarring. But yeah, an outro video would be cool. You could reference like 2012 ACS,
2012, 2024 ACS,
2024 ACS, so that in 6 more years, if we're still doing this, it'll be stale.
It'll also be stale.
It's been over a year. I can't believe we're still doing this.
Yeah.
I mean, I can, because you guys asking questions are just really great. We really appreciate it.
Yeah. It's you guys who continue to come ask us questions. You tell your friends to check out the live stream if you have questions, and that's what keeps us coming back here to answer questions.
Hopefully we're doing a good enough job. I hope we're giving you the best answers we can. We don't know everything. We try to admit when we don't. I don't know what else we can say. We're grateful for everybody who keeps coming, and this is fun engagement for us. It's good for us, for our company, and we enjoy it. So
yeah.
Absolutely. So thank you everybody again for another episode. Leave a comment on YouTube on the comment section. If you have another question, we'll either answer it in the comments or we will answer it in the next live stream, which probably is next week. I guess we're probably next week. Yeah. It's mostly back to normal time ish.
Yeah, mostly.
So this is a weekly thing we like to do. Anyway, I hope everybody has a great weekend. I hope everybody has a great rest of whatever day it is in your time zone, and take care. We'll see everybody next week.
Bye.